Good afternoon, HVAC team. We're going to go ahead and move on into Unit 31, or I should probably say Chapter 31. In the old book, they refer to them as units, so now I'm kind of possibly throwing some people off, but Unit 31 is Chapter 31. So let's go ahead and jump into that. So Chapter 31 is basic electricity. The objectives are explain how the structure of the atom affects electricity, discuss the difference between a conductor and an insulator, explain the difference between direct current and alternating current, list the characteristics of electric current that are commonly measured and the units used to measure them, explain the relationship of potential, current, and resistance in an electrical circuit, discuss the three elements required to make an electrical circuit, explain the difference between series, parallel, and series parallel circuits, use Ohm's law and or the power formula to calculate values for volts, amps, ohms, and watts. So conductors and insulators. So the first three energy levels are filled, leaving one electron in the outermost energy level. Electrons can flow through some materials more easily than other materials. Atoms that have just a few electrons on their outer energy level make good conductors because those electrons can more easily become free electrons. So having few electrons in your outer level makes you a good conductor, which is why copper is such a good conductor, because it says here the first three electron energy levels of a copper atom are full, but the outer level has only one electron, making it very easy to become free and making copper a good conductor. Examples of static electricity. Lightning is a powerful example of static electricity. Lightning occurs during a storm when cloud particles acquire large amounts of charge as they rub across the ground. Meanwhile, the ground has built up an opposite electric charge. A lightning bolt is created when the difference in charge becomes strong enough and the cloud gets close enough to the ground for the electrons to jump. Electricity, producing dynamic electricity with batteries or generators. So batteries generate electricity by turning chemical energy into electrical energy. Two chemical reactions take place in a battery. One gives off free electrons and the other absorbs free electrons. A car battery is an example of a typical wet cell battery. Generators use magnetic and mechanical energy to create electricity. When a magnetic field is placed near a conductor, the free electrons in the conductor line up with the magnetic field. Current, voltage, wattage, and resistance. So current is measured in amps. Electric potential is measured in volts. Electric work is measured in watts, and then resistance is measured in ohms. So the Coulomb is the measure of electrical charge. 1 Coulomb is equal to the charge of 6.241506 times 10 to the 18th power of electrons. Excuse me. The ability to make current flow is called electromotive force or potential. Potential difference provides the electrical pressure that makes current flow possible. The ability of electricity to do work depends on two factors: voltage and current. The watt is a measure of the rate at which electrical work is done. Wattage depends upon both voltage and current. A watt is defined as 1 amp of current flowing at a potential difference of 1 volt. Wattage can be calculated using the formula of volts times amps equals watts. The ratio of voltage to current is the resistance, and it is stated in ohms. Ohms are represented in formulas and equations as R for resistance, or the Greek letter omega. And that omega symbol you'll see on your meters. On the ohms function on your meter, you'll see that omega symbol, and that's the function that you want to go to do a resistance reading. The resistance of a conductor is affected by the physical properties of the material, the cross-sectional area of the conductor, and the length of the conductor. Alternating current. The frequency of AC current is the number of cycles per second. Frequency is measured in hertz. 1 hertz is equivalent to 1 cycle per second. In the United States, 60 hertz power is standard. In Canada and many other parts of the world, the standard is 50 hertz. The number of these waveforms occurring at the same time is called the phase. AC is available in single phase and 3-phase. A single phase AC circuit requires only 2 wires. A 3-phase circuit requires 3 wires, 1 for each phase. I remember as an apprentice, I was asked once if a unit was single phase or 3-phase, and I told the guy straight out, like, I'm not sure how I would figure that out. So he told me, oh, just look how many wires, are in the disconnect. So I opened up the disconnect and I was like, oh, it's 2-phase. And then the guy was like, he just laughed. He was like, it's single phase. And so that's what I realized I had messed up. So basically, you're gonna need 2 wires for single phase because you gotta have your hot and your common, or your hot and neutral. And then you need 3 wires for 3-phase. So there is no 2-phase, there's single and there's 3-phase. You see 2 wires, it's single phase. So don't go out there and look stupid like I did. But yeah, so the voltage used in an AC circuit changes constantly. The average voltage supplied is 0 because the 2 halves of the sine wave cancel each other out. Therefore, AC voltages are stated in effective voltage. The DC voltage that would produce the same heating effect in an electric heater is established as the effective AC voltage. Comparison of AC and DC power. Transmissions of large amounts of power involve unavoidable line losses due to the resistance of the wires. The power loss in the line is calculated using the formula I to the second power times R. Keeping the current, or I, low is the key to reducing line loss, or keeping the current low, or your amperage low, is key to reducing line loss. By utilizing high voltages, the power can be transmitted by using relatively low line current, thus minimizing line loss. In a DC generator, the magnetic north and south poles are placed in the housing, or the stator, and the windings located in the rotor in the rotor generate current as it spins. So the windings are inside of the north and south poles, or the positive or negative poles, rather than the other way around. So like on an AC generator, AC generators spin the north and south poles with the rotor. So it's the opposite. One has the windings in the middle, and then the other one has the windings on the outside. The AC voltage, or the AC generator, has the windings on the outside. So AC generators can be designed to more easily produce the large amounts of power required of large electrical power plants. So here it is right here. So on the, I'll just make this bigger real quick. On the DC generator, the south and north poles are in the stator, and then the windings are in the middle with the rotor. And then over here in the AC generator, you have the windings on the outside with the north and south poles spinning in between on the rotor. And this way would be able to generate more power than with the DC. Electrical circuits. So what do you need to have a complete electrical circuit? So these are your four components: your power source, your electrical loads, your path for current to flow, and then your switches. So an electrical power source can be provided by a battery or from a building's central electrical system. Batteries supply DC power, while most buildings have AC power transmitted from the local utility company. So that would be the plug in your wall coming from Edison. Electric loads convert electrical or electricity into useful work. The most common loads for HVAC systems are electric motors. Uh, motors drive the compressors, fans, and pumps. So the load is the part that uses the energy or the electricity to do work. In your house, the load would be, I don't know, light bulbs or your TV, whatever's actually using the energy. So you got your source, you got your load, then every electric circuit has at least two wires, often indicated as line terminals, L1 and L2. So those wires are your conductors. You have to have a conductor or your path for current flow, that's your conductor. So let's say, I like to use a vacuum cleaner, for example, to show you kind of how the whole circuit works. So you have your source, which is coming from the wall, which is what you plugged your vacuum into. Then your vacuum itself would be the load. The cord on the vacuum would be the path for current to flow. And then last but not least is a switch. So the switch is a device to turn the load on or off. The switch may be manually operated, such as turning on the light switch when entering a dark room, or the switch may be automatic, such as a thermostat that turns the unit on and off in response to the surrounding temperature. So going back to the vacuum example, the switch would be on the vacuum. A lot of times it's like something you push with your foot, like down towards the bottom, or sometimes it's just a little switch on the back. But those are the four basic components that you need for a complete electric circuit. Path of current to flow and switches. So over here, let me just make this a little bigger. So over here, you have a light. So principal components of a simple circuit, a closed circuit with current flow through the load. So again, the light would be the load, but this particular load has a switch. So in this example, the switch is closed, which is why we have a complete path of current flow and the light is on. Then over here, no current flow in an open circuit. Well, now the light is not on because we are plugged into our source. We're going to imagine that we're plugged into our source, but our switch is open. So we don't have a complete path of electricity. The electricity comes through here, it comes through here. It comes through here through this conductor. It wants to continue to go over here and energize that light and then come back through neutral, but it's open. So that's why this light is off. This light is on because we're making contact and we have a complete circuit. So we have our source, we have our path, we have our load, and we have our switch. This one is closed. Sorry, this one is closed, this one is open. Electrical circuit operation. A simple circuit consisting of a source, a path, a load. A complete circuit has continuity. It has a continuous path from the source to the load and back to the source. So that's what continuity is having that continuous flow of electricity. So same thing, this time we're using a battery rather than a plug, rather than a plug going into the wall outlet. So the battery is our power source. We have the energy coming out of the battery into our light bulb, and then back to neutral. And we see our little squiggly lines there letting us know that our light is on. And now our light is off because we have an opening in our circuit right here. Had there been a switch right here, it could be closed whenever we wanted this light to come on, and then it could be opened up again whenever we wanted this light to go off. At the moment, there's no switch. There's simply an opening here, so we do not have a complete circuit. We have an open circuit, and we lost our squiggly lines. And so over here, they're just showing you an example of both. Well, no, actually, no, both of these do have a switch. The switch happens to be open on here, so our power is coming out, going over here. It wants to continue and complete the circuit, but it can't because this switch is open. In this example, the switch is closed. So we have a complete circuit, and we got our squiggly lines back. Our light is back on. Series circuits. The voltage used by each device in the circuit is proportional to its resistance. Devices with a higher resistance receive more voltage, while devices with lower resistance receive less voltage. You know what? Let me go back. I want to say something else about series circuits. So series circuits, current flow in a series circuit, voltage and resistance in series circuit. Okay, so in a series circuit, all of the loads in that circuit are connected to one power source. Or there's one, better yet, there's one path from the power source. So the first guy in line gets the power from the source, and then each load after him gets its power from that load. So one example I'd like to use is Christmas tree lights. Back in the day, they used to make Christmas tree lights in series. So if one bulb went out, the whole string of lights went out. And then you would have to go and find which light bulb went out and change that bulb, and then all the lights would come back on. So they got smart, they stopped making them like that. They're actually in parallel now. So with parallel, you have each individual light bulb has its own path or its own connection to the power source. So if one light goes out, all the rest of them still lit because they have their own power source. It's coming from the same source, but they have their own connection to that source. So that's the difference between series and parallel. It's almost like holding hands. You know, I've done it in junior high school. I really wasn't into stupid stuff, but I don't know. I got talked into it. But these girls was sitting around shocking themselves. Like somebody had made this thing. Some dude made this some little device, and then you sit in a circle and hold hands, and then it shocks one person, and it goes through the circle, and everybody gets a quick little jump. So we were all in series, and also we were all kind of stupid, but that's how series works. And then parallel, each of us would have to have our own connection to that power source. Parallel current flow and parallel circuits. So yeah, we know the difference. So Ohm's law. Ohm's law is something that I wanted to talk about too. So Ohm's law calculations for a series circuit. So the total resistance of a series circuit is the sum of all the individual resistances. So if you had a circuit, a series circuit, like let's just go back to the Christmas tree lights. And let's say we were getting 3 ohms on one light and 3 ohms on another light and 2 ohms on another light. The total resistance of that circuit will be 8 ohms. It's just simply adding up all the ohms. For a series circuit, it's a little different for a parallel circuit. So here's Ohm's law. These are the Ohm's law formulas. So potential or electromotive force is going to be measured in volts. So to find the voltage, the formula is voltage equals current times resistance. To find your current or your amperage, that's going to be amps equals volts divided by ohms. Or to find your resistance, which is measured in ohms, is going to be ohms equals volts divided by amps. So this little chart is cool, you know, take a picture of it, write it down, you know, that's definitely, I mean, it's all accurate, it's all correct, but there's a table that kind of makes this a little bit easier if you know how to use it. So I wanted to show you guys this table. So this little triangle, or sometimes you'll see it in a circle, but this says everything you need. So how do you use it? You simply take your hand and cover up the component that you're trying to solve for. So let's say we're trying to figure out what the amperage is. So I is your amperage or your current. They use an I for intensity, the intensity of the current flow. So I is current. If we wanted to solve for I, we would cover up I, right? So pretend this hand is bigger than that and it's actually covering that I. What do we have left? We have a V over an R. So we know in mathematics, a number above another one, you know, if we have that line right there, that means to divide. We have a V above the line for our voltage, we have our R below the line for our resistance. So we know if we cover up, if we're trying to solve for I, let's cover that up. And then what that leaves us with is V over R, or V divided by R. So that tells us that current equals voltage divided by resistance. Let's say we wanted to solve for voltage. We want to know what our voltage is. So we cover up the V, right? And what does that leave us? That leaves us an I right next to our R. So we know in mathematics, when you have a number right next to another one, that's telling you to multiply. So V is V equals I times R. Or if we want to solve for R, we simply cover up the R. We're taking the R out of the whole thing. We cover that up with our hand. That leaves us with a V over an I. So that's telling us R equals voltage divided by current. So this little table, once I was shown that table, it makes it like impossible to forget how to solve these problems, because you take your hand and you cover up one component and it leaves the other two, but it leaves them in a specific arrangement. If one is over the other, you know that's divide. If one is next to the other, we know that's multiply. So this table is like the Bible for Ohm's law. It just kind of breaks it down without feeling pressure to memorize an entire chart, which also isn't that complicated. It just depends, you know, different strokes for different folks. Some people can look at this and be like, okay, I got that. But I tend to forget stuff. But that little chart makes life a little bit easier. So series circuit resistance, current, and voltage. The total resistance of a series circuit is the sum of all the individual resistances. The current is the same throughout a series circuit. The voltage drop across each load in a series circuit is proportional to its resistance. So, like I said, you know, this is a series circuit. So you got 4 ohms here, 5 ohms here, 6 ohms here. That's giving you a total of 15 ohms. Then over here, they're giving us the same thing. We got 4, 5, and 6. So we have a total of 15 ohms. They're giving us our voltage. So this is a 30-volt circuit. And then there's 2 amps going through each load. But yeah, it's, you know, it's the same thing. When it's a series circuit, the total resistance is the sum of all individual resistances. Calculate or calculations for a parallel circuit. So this is a little bit different. If there are more than 2 resistances, use the following formula to solve for the total resistance. So down here, you have that formula. So for me, not being a mathematical genius, I was taught how to calculate the total resistance of a series circuit using the VERP table. So I drew a, I'm gonna stop this screen share real quick. So I drew a little my little version of a VERP table on the board. So I'm gonna go ahead and explain that to you real quick. It's not a complete VERP table because I left P out because we're not really worrying about wattage at the moment. So we're just gonna focus on solving the total resistance for that circuit. So let me try to make that, I guess that's as good as it's gonna get. All right. So this is my VERP table. This is our little Ohm's law diagram. We're gonna hold on to that. That's the Bible. And this is my parallel circuit. So in my parallel circuit, I have 3 loads. These little squigglies are my loads. This is my power source right here. So I got this battery. It's a 60-volt circuit. So I got my 60 volts going through all the loads. And I have each different load has its resistance. I already got the resistances written down. So we have 3 ohms here, 4 ohms here, 5 ohms here. So on my little VERP table, I have resistance 1, resistance 2, resistance 3, and then my total in this column. So in this first column, I'm gonna go ahead and put my resistance for the first load, which is 3. And a quick tip, when you're trying to check your work, one rule of thumb is on a series circuit, the total resistance is always going to end up being lower than your lowest resistance in your circuit. So if my lowest resistance is 3, if I get anything above 3, I already know I went wrong somewhere. So so let's keep moving. So I have 3 ohms for resistance 1. Resistance 2 is 4 ohms. So I'm going to put my 4 in here. Then resistance 3, that's going to be 5 ohms. So I got my 5 ohms, or I got my 3 resistances. I don't have my total yet because it's not a series circuit. If it was series, I'd just add these up and I would have my total right there. I'd just put 13 here and be done with it. But 13. I told you I'm not a mathematical genius. Anyway, I would put my total there if this was a series circuit, but it's not. It's parallel, so we're gonna we got more work to do. So our voltage is 60. That's a given. So we're gonna put our 60 here. We're gonna put our 60 there because the 60 volts going to all our loads. So 60 all the way through. What's our total voltage? You guessed it. It is 60. So our 60 is a given. That was our that is our voltage. So now we got to figure out our resistance, our current or our amperage. So to figure out our amperage, we're going to refer to our diagram over here. And remember, I is our amperage or our current. So I'm simply going to cover up I, and that leaves me with a V over an R. So that means I equals V divided by R, or amps equals volts divided by resistance. So my voltage divided by my resistance on resistance number 1 is going to be 60 divided by 3, which is going to be 20. So I'm going to go ahead and put 20 right here. Then over here we got a 4, so 60 divided by 4, that's going to give us 15. So we're going to put our 15 right there. And then one more time, we got a 5 on this load, so 60 divided by 5, that's going to give us 12. And so our total over here will just be added up. So that's going to be, what is that? 47. So we add all of our amperages to get our total amperage. Our voltage doesn't change. Our voltage was 60 throughout that whole circuit. So we got our 60, we have our 47. Now we need our total resistance. This is a number we've been trying to get this whole time. And again, we're not going to just add these up and be done with it. That would be for a series circuit. What we're going to do here is we're trying to solve for R. So we're going to cover up R, and that leaves us what? That leaves us with a V over an I. So that means R equals voltage divided by resistance. I'm sorry. amperage. So, my bad. So me not being a mathematical genius, I'm not going to do this in my head. So 60 divided by 47 is what? 1.27. 1.27 is our total resistance for this entire circuit. 1.27 is in fact a smaller number than 3, so we know we're in the ballpark because our total resistance is supposed to be it's always going to be lower than your lowest resistance. But that's not the only reason why I know it's correct. It's because we did the math. So there it is. That is how you get the total resistance of a parallel circuit. So you see why it's so important to utilize this little diagram when it comes to these little mathematical equations regarding electricity, you know, ohms, volts, and resistance. You can lean on that. You could just lean on that. You don't have to worry about memorizing what does what. The more you do it, the more it'll stick. The more, you know, as we move forward with some of these assignments, it'll start to stick. But when in doubt, draw it out. V over I next to the R, and you can figure out any of these equations. So that is it. So our total resistance in this example is 1.27. That's how you do the parallel circuit. That's how you add the resistance, or not add, but calculate. Okay. Moving on, what's next? So in summary, electricity is the flow of electrons. Electrons are negative subatomic particles that exist on the outside of an atom. Electron flow is a chain reaction with electrons moving from atom to atom. Electrical potential is the ability to produce an electrical current and is measured in volts. Resistance opposes the flow of electrons and it is measured in ohms. Electrical work is affected by potential and current flow and it is measured in watts. Resistance and current move opposite each other. A series circuit has only one path for electron flow. Voltage stays the same in a parallel circuit. Adding loads in series increases circuit resistance. Adding loads in parallel decreases circuit resistance. Ohm's law and the power formula can be used to determine voltage, amps, ohms, or watts, as long as any two values are known. Just want to go back to one thing real quick. So it says adding loads in a series circuit, adding loads in series increases circuit resistance, and then adding loads in parallel decreases circuit resistance. The reason for that is I like to imagine like cars on a freeway. The more cars you put on that freeway, let's say you're on a freeway and it's only one lane open. The more cars you put on there, the more resistance there's going to be. But let's say you opened up all the lanes. So now all these cars got their own lanes. It's going to be a lot less resistance. So that kind of helps me grasp that concept. So anyways, that is the end of that. So like I always say, read chapter 31. It's going to go a lot deeper than what we just did, but hopefully that was helpful. Chapter 31 will be on FlexiQuiz tomorrow. And just ate lunch. I probably should have did that after this, but anyway. So have a good one, and I'll check in with y'all next time.